believe we'll have a few more folks filter in. Welcome everyone to today's BSUC. Today we have Jordan Pratt. He's a mechanical engineer with a passion for energy efficiency. Jordan manages a wide range of emerging technology field tests and market transformation efforts for NEA, the Northwest Energy Efficiency Alliance. Recently relocated to Idaho not too long ago. And so he's working with the Idaho Power Energy Efficiency Program. He has experience analyzing complex mechanical systems, as well as installing, commissioning, and testing a variety of equipment and systems. I've attended a couple of his lectures over the years. He's really good, so we're fortunate to have him with us. So, Jordan.
Thank you, Dylan. Appreciate it. Thanks so much for coming out, especially on this beautiful Boise summer day. Feel right at home. Got to dust off my rain jacket. As Dylan mentioned, I'm originally from Portland area. Moved out a couple of years ago. My family and I absolutely love it out here. This high desert is the climate for me. Definitely not going back. Energy 350. We implement Energy Trust of Oregon's industrial program back in Oregon. So we have a team of about 50, 55 or so engineers back there. A small team out here. A few of us serving Idaho Power. Love what we do. A lot of commercial and industrial work. But I spent a good chunk of my career doing emerging technology field testing, which is mostly what I'm going to be speaking about today. So any technology that the utilities are interested in as a resource, they like to kind of kick the tires. They're pretty conservative in terms of new technologies, and they want to make sure what they're paying incentives on and recommending to their customers hold up in the field. So I've run a dozen or so heat pump field tests in the last 8 years. So heat pump water heaters, commercial heat pumps, a handful of other kind of more exotic heat pump systems. So yeah, that's kind of my sweet spot. What I love doing is seeing how things actually perform in the real world, finding areas that they can improve, whether it be from the end user standpoint or the design and construction industry. There's oftentimes some benefits and some challenges with new technologies. So today, what I'm hoping to be able to help show you, or at least show you, is some data that may help you believe that air source heat pumps perform really well in cold climates, and that there's just a wealth of data out there that I think both the energy modeling, building simulation community and the design and construction community could rely on for some insight in the way that they look at new technologies and just in their general business. So those are kind of my big things that I'm going to talk about today. All right, see if that's where things. All right, first off, so one of my main clients that I do this emerging tech for is the Northwest Energy Efficiency Alliance, or NEA. They're a nonprofit organization of about 140 utilities across the Northwest, including Idaho Power, Northwestern Energy, and Montana, so a few of these kind of inland Northwest regions. But they basically are all about market transformation. So they work kind of ahead of what's available right now a little bit and try to bring new technologies to utility incentive programs. But they can take a little bit more risk and kind of pool that risk across a bunch of little utilities and some bigger ones, so that they can use those resources to check out new technologies and do some great research. So I'm on behalf of NEA today, and Better Bricks is their commercial facing website where a lot of the resources that I'll be discussing are housed. Okay, just quick agenda: why air source heat pumps in cold climates? What is very high efficiency DOAS, or dedicated outdoor air system? How heat pump systems perform in the field, and in particular in cold climates, and how, hopefully, a little bit into how field data might be useful to energy modeling, to building simulation professionals. All right, first off, air source heat pumps. Sorry to bring you back to thermo, but I know you probably all know what an air source heat pump is, or a heat pump is in general. But it's basically a refrigerator or an air conditioner that can run both ways. It has an evaporator, which absorbs heat, a condenser which rejects heat, and a compressor which makes the whole thing go. And some sort of a metering device. If you like pressure enthalpy diagrams, this just kind of reminds you we do work along with a compressor, but what we really care about if we're in heating mode is condensing, rejecting heat. That is your heat sink. That's where you're dumping heat to, and then your heat source happens here at the evaporator. If we care about air conditioning or cooling, it just gets flipped, and we have a heat sink down here. Oh, sorry, heat sink is still up here, down here. Heat source is down here. But our goals can switch how this thing runs. Some people are like, but why an air source heat pump in cold climate? Don't heat pumps kind of suck when it gets cold outside and your heat source is low? And it's a good question. The correct answer is, of course, heat pumps never suck. They just pump heat. My last bad joke for the day, for sure, or at least for this session. I'm a full stream of them at home. But anyways, okay. So before I get too far into that, air source heat pumps is, of course, one variety of many different kinds of heat pumps. This is kind of a very brief taxonomy of all the different heat pumps. We've got sectors, so residential, commercial, industrial, high temp heat pumps. Sometimes we talk about the heat source, so an air source heat pump, a ground source heat pump, a water source heat pump. If a working fluid, how the heat or cooling is delivered, either by air or water, most common. Form factor, whether it's packaged or split. Configuration, whether it's moving air via ducts or ductless, or some combination of the two. Is it doing space heating or water heat, space conditioning or water heating? A lot of heat pumps do one of the two, some do both. There's combi units. And then functions, constant speed, variable speed. If it's a cold climate unit, does it have additional features? And then zoning, is it multi-zone or single zone? So anyways, when you hear the word mini split, it's a lot faster to say mini split than residential air source, air delivery, split system, ductless, space conditioning, variable speed, single zone, right? That's what we call it, multi-split. But we usually talk about heat pumps, in some version of these taxonomy. So air to air, air to water, ground to water, ground to ground. No, that's not a thing. But there are some more exotic ones. Like I'm not even mentioning. There's engine-driven gas absorption heat pumps. Heat recovery chillers, absorption chillers, all these kind of things. But these are probably the most common. Here's one version, super common VRF system, which would be a commercial air source, air working fluid, combination of duct to ductless, split, and for space conditioning. But we just call it VRF for heat pump of some kind, commercial heat pump. That's our office building, by the way. Proud of the system because we designed it and have been metering it like a lab experiment for the last 5 years. So, yeah, we're going to be talking mostly about air source, variable speed, cold climate, some space heating, some water heating, some residential, some commercial, but mainly air source, variable speed, cold climate units. All right. So back to the heat source and how efficient heat pumps are. Carnot efficient determines the maximum efficiency of a refrigeration cycle. So it's determined by the high temperature source divided by the difference between the high temperature and low temperature source. So the lower the cold temperature source, the bigger this difference and the harder it is to have a good theoretical efficiency. We know that. Makes sense, harder to pull heat out of a small space or a cold space. Boise is got a climate zone 5B, cold, dry, high desert climate. Its ASHRAE 99.6% design. Dry bulb is 11 degrees Fahrenheit, so pretty cold. Extreme maximum usually about 5. But if you look at the average temperature of the winter, even just like December, January, February, about 34 degrees. If you look at Minneapolis or Bozeman, climate zone 6, even then it's like in the low 20s, low to mid 20s. So the average temperature is actually not that cold. And when it comes to energy performance, that design temperature doesn't all that matter that much. That matters for your load calcs and maybe backup heat if you need some. But really, that's the performance number that matters. That's thousands of hours a year in Boise, the winter, a good chunk, well over half of our hours a year, 34. So if you just, and then I'll just mention, a lot of people will say, what about ground source, about water source? Yeah, it's great. It's 50 in the winter, so it's a bit better. So what is that math? We do the math on an air source. Carnot's about 14.7. That's the best you could do. Of course, we never get to the best. There's some engineering decisions and challenges. Ground source about 26. So yeah, it's better. And I would agree in some applications, especially really big applications and really cold climates like in the Arctic and climate zone 7 and 8, once you start getting up there, it gets even more challenging to do air source. But we're working with a pretty good heat source here in this climate. Here's a performance curve of our office building. I have the best details on it, but it's not a cold climate VRF system. It's about 10 tons, just kind of off the shelf VRF from 5-6 years ago. At 34 degrees, where that blue dashed line is, we have 125% of nominal capacity, so about whatever, close to 12 tons, 150 MVH. 100% of max capacity. That's as much as it can deliver. And its COP is about 3.8, so it's 26% of Carnot efficiency. Probably some room to grow there, but all that to say is a lot of performance at a lot of the year. And then even when you go down to design, it's still 100% of nominal capacity. It's still delivering 10 tons, 120 MVH capacity with a COP of almost 3. And again, that's not a cold climate unit. That's just kind of off the shelf. And it can also go down to -15, which is, I think, a 50-year max here. So still delivering constant heat down to -15. I'll speak a little bit more about real cold climate units later. So why air source and not a better heat source like ground source? Well, my experience has just been in working for utilities for market transformation, where we can apply these across lots of buildings and lots of applications cost effectively. Air source wins almost every time in terms of simplest. You can do it. You don't need land. You don't need a parking lot to hide a ground loop under. Widest applicability, even in cold climates. I think 9 times out of 10, the design is much easier and the performance is very good. And yeah, that's partially my own preference, but I think it stands out. All right. What is very high efficiency DOAS? Well, it's a commercial HVAC system that applies the heat pump technology. Talking about this because I have a ton of field data from this, 20-something sites where I have HVAC sub-meter data. Most of them have detailed annual energy models as well. So just have a lot of experience and a lot of data that I can share based off of this system. But today, I mostly want to talk about the heat pump performance, not the overall system. But in general, across these 20-so projects, we saw almost 70% HVAC savings relative to the existing system with code minimum equipment. And then whole building savings, almost 50% savings. So basically cut the building energy use in half across all these projects. Briefly on the concepts of very high efficiency DOAS, decoupling the ventilation air from the heat pump and spacing the applications, commercial applications makes a lot of sense. You can optimize each of those systems. Adding exhaust air energy recovery is absolute no-brainer and a win even in more mild conditions, but especially in colder or hotter climates. There's a lot of ventilation load in some commercial buildings, especially higher density occupied ones. And when you can get that heat or that heat rejection for free, it takes a lot of load off your heating and cooling system. Allows you to really select an appropriate size and a cost-effective heat pump system, even in cold climates. So when you can cut out 30% of your design heating load, you can size a smaller piece of equipment that can still hold up, and you don't have to basically have 150% capacity just for that 1% a year. And then, yeah, sizing of systems, I won't get into it, but it's a big deal. HVAC systems are chronically oversized. And in particular, DOAS systems with heat recovery tend to get oversized a lot because designers are conservative and don't want to take advantage or don't want to take credit in their load calcs for the ventilation heat recovery. But that doesn't have anything to do with heat pumps right now, at least. Here's an old figure with some of the different demonstration projects we had, mostly small to medium buildings, offices, schools, restaurants, dormitories, a couple in Montana. We've done a couple in Eastern Oregon, Eastern Washington, Bend area, very similar climate, even a little colder, higher elevation in Boise. So I'll speak a little bit to a Bend project that I think will resonate with this climate here. Noisy figure, but basically commercial buildings, their EUIs are all over the place. But the big thing to point out is this is where that 69% HVAC energy savings and 48% building energy savings come from. We got a lot of data. Every one of these has an energy model. Every one of them has HVAC sub-meter data, maybe pre and post for at least 12 months. And so we were able to calibrate our energy models and get them very similar. But anyways, we're very confident in the results of these just because of how much data we've collected out in the field. And then another takeaway is almost boringly predictable results. Almost every project that we did in offices and schools ended up with an HVAC EUI around 11. So regardless of whether the building had a EUI of 100 or 30 to start with, we ended up with the HVAC EUI of about 11. So very consistent results. And this is DOAS, which of course, has some benefits above just the heat pump performance, but that's a big part of it. All right. Some more on available field data. I don't know, Dylan, will you share out these slides if I share them with you? I threw a bunch of links in here just because I want to make some resources available, and I think they're really cool if anybody's interested. But there's a whole bunch of cold climate heat pump testing data out there. We did a heat pump water heater field testing up in British Columbia back in 2018. Some great data there for residential water heating. NREL had a really cool cold climate air source heat pump field demonstration. Minnesota Center for Environment and Energy CE has done some great cold climate VRF for commercial air to water heat pump and residential applications. PNNL just implemented with Guidehouse, implemented a large cold climate residential central forced air system heat pump testing through the DOE heat pump challenge. We were a subcontractor on that and did about 8, 9, some of them up in Minnesota, upper Minnesota and Michigan, really cold climates. Really fascinating results from that one. ISERTA, there's a great air to water heat pump white paper. I know of some ongoing and future research that threw some links in here as well. But anyways, there's just a wealth of field data that's been collected on cold climate heat pumps. So if you ever want to dig into that data, I think it's worth it. Let's see on time. All right, I'm doing pretty well. There's going to be a lot of data here. I'm going to try to go slow enough so that I don't overheat like a cold climate heat pump does when it gets too cold outside. But there's a lot of high level data in different cold climates that we've done and other folks have done. And I just want to give you an idea of what kind of data is out there. And I think will kind of whet your appetite of what could be useful. So dorm rooms in Trapper Creek up in, I forget what part of Montana, but I think it's like the northwestern part of the state. Climate zone 6B, very cold. Had electric forced air furnaces, no mechanical exhaust other than a couple exhaust fans, so bad indoor air quality. Installed a bunch of single speed heat pumps. Still kind of breaks my heart. There was, I don't know, some kind of government Buy America type of deal where you couldn't buy any overseas equipment. So we had to go with the best that was available, which is single speed, non-cold climate in a very cold climate. And it still cut the energy use in half, the HVAC system. I think there was a lot of potential for better performance. But even then, in some applications, you don't even need cold climate. In a cold climate, just have to design well. And again, this solution applied that very high efficiency DOAS with 85% exhaust air energy recovery. So that was able to downsize some of that backup electric resistance that we needed in the cold. Because if you're eliminating almost all your ventilation load, it kind of decoupled from your outside air temperatures. Yeah, the heat pumps still have to pull heat out of it, but you don't have nearly as much ventilation load as you do if you did not have that exhaust air energy recovery. So kind of decouples your performance from the ambient conditions. Another Montana project, utility office building, wildly high energy use, all electric building, almost 100 EUI for mostly office space and a warehouse that was for utility trucks. So more than double the kind of CBEX average annual energy use. Similar situation, there was some limitations in equipment availability. That'll be a theme in rural places. Sometimes it's hard to get the best equipment. But HVAC energy use cut by 45%, total building energy reduced by 29%. Another great story, little rural elementary school in kind of central eastern Oregon. All electric heat, no mechanical ventilation beforehand, 60% energy reduction, 35% energy use, building energy use reduction. Gave them ventilation, so they're very happy about improving indoor air quality as well. Cool one about that one, it was a partnership with Bonneville Power Emerging Tech. So we had a lot of funds to really dig in and collect some great data. This is just the monthly coefficient of performance, COP of the heat pump. One thing I just wanted to point out is that was a very cold climate, a little colder than Boise, I think. Climate zone 5B, certainly a lot of days, a lot of hours in the teens and single digits. Even in the coldest winter months, December, January, February, we're hovering right around a COP of 3. Of course, when it's warmer and there's not much of a delta T, COP is high in the 5s, but annual COP of 3.5. This is something that I always love to do anytime we have enough data to do it, is just calculate the overall system performance in a commercial or a school application, which is basically just sum up all the loads, the envelope loads and the ventilation loads, and divide it by all the energy inputs and give your whole thing of whole system, basically how well did that perform. Make it dimensionless so it's COP and it's easy to consider. Before they had about a total COP of 1.88. That's better than a lot of the electric resistance because cooling has higher performance and some of it was heat pump to begin with. But we have a system COP of 3.7. So that relatively cold climate, and just kind of remember that 3.7 number is like system level COP. I'll get to a reason why that matters in a minute. Here's some other systems where we had great data, pre and post coefficients of performance. So like gas system that has like less than 80% combustion efficiency and a ton of heating and not very much cooling might have a COP of 0.85 total. A heat pump in a relatively mild Seattle climate, like a standard constant speed heat pump, might have a COP of 2 because they're using a lot of electric resistance. But across the board, I mentioned consistent results. In most climates, even in the colder climates, we're getting system COPs of 3.7 or above. And all this data is published in Better Bricks technology, HVAC, DOAS. You can find it pretty easily. All right, break even. I told Chris that fuel switching is a bad word, and which I'm not advocating for. But what I do want to say is, when does it make sense to have an electric system versus a gas system? If you have options for both, and I'd argue that money is usually what drives most people to make decisions, the economics of it. So I want to compare 3 different, very simplified technologies to kind of illustrate this point. So say you have a natural gas furnace or boiler that's about 80%, so atmospheric, non-condensing. You have an electric resistance, either zonal or electric resistance heat, which we actually still see quite a bit. And then a heat pump with just kind of average COP of 3. So just very basic across the board. Let's say gas costs about $1 a therm. Electric rate's about 12 cents. Probably a little higher than here, but I think the spark spread, the difference between the two is probably pretty similar. And let's say you have to deliver 100,000 BTUs, so roughly a third of heat output in all 3 of these situations. Just for fun, we'll also throw in the stoichiometry of natural gas. It's 117 pounds of CO2 emissions per million BTUs. Marginal Western energy grid emissions rates about 1,500 pounds of CO2 per megawatt hour. And so we'll compare the performance of these 3. What does it cost? Well, it costs this boiler or this furnace about $1.25 to deliver that therm. And that's based off of that 80% efficiency and that $1 per therm. Cost this electric resistance furnace about $3.50, so almost 3 times as much. So in this case, this definitely beats electric resistance in terms of cost. And then what is the heat pump kind of marginal performance of 3.0? It does it at $1.17, so a little cheaper. So this tells me that the COP of 3, this system, is roughly equivalent to a non-condensing natural gas system at those gas and electric rates that I mentioned. And so that's kind of our number we kind of got to shoot for if we want to break even. So it's important that we can perform even in cold climates if we can have a heat pump, that you have a COP of around that level if you're comparing to a non-condensing furnace or boiler.
So is that $1.17 number, is that normalized across the capacity of that heat pump? Because that COP is going to change depending on your outside air temperature.
Yeah, so remember what I showed you before was the annual average COP across the year. So
That's taking that into.
that's taking, well, this is just, I just made up that number because I see a lot of numbers at that or better. So I said, hey, let's just set the seasonal performance level to have to do this. But yeah, you could do this with an annual hourly model if you wanted to, and actually use the different winter and summer rates, and it would come out slightly different, but it's going to be about the same if you take that rate and apply it across all those different performance. So part of the year 2.5, part of the year 3.5, averages out 3. But that's good question though. And then on the emissions rate, roughly the same story, triple the emissions. It roughly follows the cost of electricity versus gas. 44 pounds of CO2 to deliver a therm for electric resistance is 3 times as bad as the non-condensing furnace. And the COP basically breaks even. So you basically breaking even with cost and emissions. And if that changes at all, if electric or gas goes up relative to each other, which I'm not advocating one way or the other, that number will change. And of course, emissions, I think pretty much across the board, those are going down marginally and on average. So I think that number means that COP could probably go down over time and still break even. All right, I'm going to breeze through these, but this is just some very cold climates that had metered load and input energy and actually quantified COP out in the field. This is a NEEP, Northeastern Energy Efficiency Partners, Ridgeline, a bunch of people partnered on it, but they tested a bunch of commercial VRF systems in the field. This is outside air temperature, gets into the just under 10, so pretty cold for the whole day. COP is just kind of hovering around 3.5 to 4, average of like 3.5 on the day. It's pretty good performance. They had some mixed results. There were some real bummer ones that had been installed 10 years ago that weren't installed well, that performed with the COP under 2. So definitely a mixed bag, and installation matters, design matters a lot. But there was a lot like this, which even in very cold conditions performed well. This is a Minnesota CE. I love these normalized V shapes. They're great. Taking field data, taking an average daily outside air temperature and comparing it to average daily energy use, normalized to square footage. What's so great about this? You got a small office here in Minnesota, a large office in Minnesota. We can take these and say, okay, like I've got an energy model. I'm modeling a large office building in Montana, and is there any field data out there? Well, I can go check it here and see, like, am I ballpark? Because most of the time, these normalized rates don't vary a ton, even across buildings that are 20 years difference. The numbers come out pretty well, so it's a good gut check if you're doing any building simulations. A lot of data out there. This is from the same study, so commercial air source heat pumps in climate zone 6 and 7 even. Some of these were in northern Minnesota. A lot of really cold days, so a few hundred hours down here below 0, some in the negative 10 to negative 20 range. COP still hovering right around 2 in these coldest. But one thing I wanted to kind of point out here is this is Minneapolis, I think, which is climate zone 7, I believe. Anyways, lots of hours every year in the negative, so it's certainly colder than here. And 90% of their winter hours are warmer than 20. So even though that they get into these very cold conditions and really have to worry about some pretty bad Arctic cold snaps, most of their performance on an annual basis actually happens in this range. This is like, you can see the numbers here, 1,600, 1,700, 700. This is like 4,000 hours a year right here. And the COP is, getting up in the mid 3s here. So that's really what matters for performance, even in colder climates than Boise. This is a residential heat pump water heater study back in 2018, done up in high elevation in British Columbia, so very cold, climate zone 7 and 8. Again, outside air temperature versus COP this time, but just shows kind of the range. Water heating is kind of goofy because it depends a lot on usage patterns and not just on outside air performance like space heating does. So it's a bit messier usually when you compare it this way, but it gives you a sense of the range of COPs. Bigger. What was interesting here, this is like stand-in units, so split system cold climate heat pumps, and they love cold return temperature. If you give it warm, they don't really perform very well because it's a CO2 transcritical cycle. COP, there was a much better correlation with actually daily water usage than outside air, even though it was a heat pump, which is partially speaks to how good a performance it has in cold climates, but also just the transcritical cycle needs really cold water. Anyways, the bigger dots were more water usage. So like if you're looking at CO2 high temperature water applications, a lot of times you need really high water users for them to perform really well. So that happens in industrial and large commercial applications. That's really important. Let's see, this is a really large database of residential heat pump, both water heating and space heating, managed by DOE, PNNL, I think put this together. But what is it, a couple hundred sites, 170 different sites around the country. Quite a few cold climates, some in Idaho, a couple up here in British Columbia. I think that was that same study. Some in Eastern Washington, getting in the climate zone 5B, and then a lot in Northeast. But what's so cool about this, they have every CSV file, hourly data that was collected across, 50 different sites, or no, 170 sites, many different places. So if you ever have need for residential data and you want to geek out on it, it's publicly available. Yeah, okay. Shifting gear just a little bit, I wanted to do a quick exercise in sizing, because I mentioned that performance really matters in that middle range. That's when the most hours of heating happens. But it does matter to keep the building comfortable when it's really cold outside. So air source heat pumps, well, do we have to have a lot of electric resistance backup or gas backup or something in cold climates? This is in Bend, Oregon, about a 6,000 square foot office building. They're a little colder, a little higher elevation than Boise, but other than that, very similar weather. So 5.5 instead of 11 design day. So we did load calcs on this building. First thing was crazy. We did load calcs for the existing building with no heat recovery, and we got 180 MBH of design load. And we were being pretty conservative. We weren't trying to get too aggressive. And so 15 tons ish. They had 25 tons, almost 300 MBH of gas heat capacity. So the system was basically almost twice as big as it needed to be. So they didn't do load counts, clearly. And then when we eliminate all this ventilation load from having exhaust air energy recovery, we get down to 10 tons. So we basically more than cut in half the size of the system. And we were actually ended up being pretty aggressive. We took some diversity and things like that. But nonetheless, it's a little nerve-wracking when you advocate for installing 10 tons of capacity when there was 25 tons, and you're kind of, well, we weren't the engineer record, we had sales. They did what we said. But anyways, this building performed great. And there was a couple weeks in Oregon where it never got above 15 in Portland and all the pipes were busting. That was 2 years ago. It was even colder in Bend in the single digits for most of the week. And that was, of course, our design day is 5.5. And so when it's -5, -10 there, that's not what you designed for. Now the physics don't even matter anymore. So you're clearly undersized. But what we found when we've been super aggressive and there's been abnormal events like the heat dome when it was 112 here, or in Portland it was, the system still performed. And that heat pump in particular at that Bend site, right, when it starts getting into these -10s, the load does start to drop off. And of course, the actual heating load goes up. So we have a divergence here. But you're still, even at 5 degrees and -5 degrees, we still have almost nominal capacity. So at 5 degrees, we're at still 100% of nominal capacity. At -5, we're at 90% of nominal capacity. So it's still there. And these heat pumps, most will keep running continuously down to -15. The cold climate ones that add vapor compression will go down to -31. And I think it's 50% capacity at that point, but it's still operating. So it's still not letting the building get too out of control. And that's what we found. And this is one example, whereas 20 degrees or 15 degrees below design temp, we still let the building shut off and float temperature down at night just to see what would happen. I love doing science experiments in the real world at the expense of my own engineer's comfort. But it's still maintained about 70 during the day. And so we found that even undersized systems, still the building doesn't go to 60. Pipes aren't busted, especially if your heat pump at least keeps running. So most of these, maybe all of them, except for the 2 Montana ones, had no backup heat. We just sized it for 99% and called it good. Mentioned flash ejection. This is a cool engineering thing. Does anybody know what causes a heat pump, an inverter-driven heat pump, just to have a minimum temperature outside? What's the problem? The engineering design challenge? Anybody know?
roll it, not sure.
Exactly. It's a heating problem. You're getting too hot. It's like you run a marathon, it gets too cold. Why can't you run a marathon? It's got overheating because you're working so hard. But yeah, the compressor, the reason why inverter driven heat pumps are so important in cold climates compared to a constant speed compressor is they can vary. They have lots more levers to pull. They can vary their suction pressure, which is what's required to deliver to suck heat out of colder and colder. So they keep going lower and lower. They just have to go run faster and faster to drive down suction pressure and still maintain a reasonable discharge pressure to reject heat through the condenser. So anyways, the problem or the way that they solve this cold climate or this cold weather performance in variable speed is says, oh, well, we just got to cool it down, right? Obvious, easy answer. So some VRF manufacturers and I think mini splits, no, I don't think mini splits do flash injection that I know of, but they steal a little bit of cool liquid and send it back to the compressor to cool it down. Others have a separate refrigerant, a different refrigerant circuit that kind of gets activated to cool the compressor down. But this stuff is like, you know, pretty common in industrial applications, compressor applications too. So anyways, really cool. This is what allows those heat pumps to keep sucking heat out at -30. Other design, I won't go too far into this, but other cold climate design things really matter where they don't in more temperate climates. Snow, something you have to think about in Western United States, like West Coast very much. Wind baffles, snow hoods. This makes a huge difference because it mainly helps reduce the amount of time these things have to defrost. So that wind ripping across there makes these coils very cold and start frosting up. Defrost, you know, these things still can provide continuous heat even when they're defrosting. They usually have a couple circuits, refrigerant circuits, so they'll run one to avoid blowing too hot of air, but they still are able to kind of keep going, keep providing heat. And then yeah, wind cables, wind baffles is going to go. All right. Why does this matter if you're a building simulation professional? Or I'd say there's probably more applications just that. That's what I wanted to focus on. And work a lot with some energy model experts. A2 Efficiency is one that I work with that just got off a call with them, and we're going through energy modeling that we're trying to model across many different climate zones, many different building types, and be able to turn all kinds of different levers. But we got to be able to ground it. And so that's where I kind of work really well with them, is have all this field data and experience and seeing like performance data across different climate zones and be able to kind of like provide us some guardrails so the energy model, doesn't go off the rails. So part of the reason that's important, we had a really fun science experiment with some of the initial demonstration projects we had, where we found a building, said, hey, we're going to do a conversion to DOAS with heat pumps. How much will we save? And we did a pre-model, did a post-model. Then this is in parallel, also doing HVAC sub-metering for the few months that we had whenever the project was happening. And then we installed the new system, and then we metered the new system for 12 months or longer. And so we had this great opportunity to say, all right, we did an energy model. We knew everything about the building, the R values, the areas, the ventilation rates. We pretty much had the answer, what most energy modelers have. They've got the building, they've got the drawings, they've got the plans. Like, can't we get it right? The energy models like have some great, prototype buildings that we can kind of go off of, and we can build this. So we did this, and this is not a shot to the energy modelers, but like we were across the board modeling way less energy use in the baseline system than we actually found after we did it. So they were way worse in reality than existing systems. And then with this DOAS, this VHE DOAS system, which there's not a lot of systems built into the energy models that kind of model newer systems, significantly overestimated performance. And so there was this big delta in the amount of energy savings we were modeling to start and what was actually seen by this field data. And so that allowed us to recreate models that were more accurate. And we did that using the field data we collected. So it's really helpful because now we have these kind of templates for the energy models that we're like, all right, we're a lot more confident in these. We've got a dozen or so of these calibrated energy models. Obviously, that can't be done in the real world very often, especially not when you're trying to make design decisions on a new building. But I think that field data can help kind of calibrate even those models when you have like new buildings with field data that's been collected that's in a similar application. All right, so what do I mean by calibrating? Well, I think probably the most common way that building simulation professionals will calibrate a model is if they have an existing building, they'll take monthly utility data, it's the easiest to get. They'll take the weather data and they'll normalize it, and then they'll compare it to their model, and they'll kind of tweak things, whether they make real sense or not, just to get the kind of monthly columns, those monthly bars to match up so that your ASHRAE coefficient of variance makes sense, and you're going to be all that kind of stuff. So that's one way to do it, and that's really helpful. That grounds you in reality for sure. And it also helps you kind of like figure out the cooling and heating dependence of your energy usage. Another way you can do it is you can take your hourly energy model and then actually collect some data, hourly HVAC data, and try to like make these V's match up. Gets pretty messy. You can see all these zeros in like cold weather, and it's hard to really tell. You can tell like, yeah, on the coldest days when it's 20 degrees outside, and the system's running all out, it's using about the right amount of energy. So that's really helpful to kind of get that V for another piece of the puzzle. This building in particular, why were all these zeros down here? Well, here's the heating load profile. And it's because they had a pretty aggressive setback. And so the system wasn't running in the coldest hours in the morning, and then it would ramp back up really hard. So there's some challenges with demand loads and stuff in that, and cities that are electrified. But that's a different presentation. One of my favorite ways is just to roll it up to daily, and sometimes zoom it out a little bit helps tell the story a little bit. So this is daily total kilowatt hours. It's even better when you normalize it by square footage, but daily kilowatt hours compared to average daily outside air temperature, and this creates this nice V modeled versus actual. So a few different ways that you can use field data to help calibrate simulations. A little bit about going back to that, all those calibrated energy models. This is kind of the basic framework where we used. Take actual data, utility data, or collected field data, actual weather data, create a model, and you calibrate that model using the actual weather data. Then you take it and you say, well, we actually want to model a typical weather data. So pretty standard. Same thing on the, once we installed the equipment, we took the actual weather data, built an actual weather model, calibrated to the actual data, and then built a typical post-conversion model. And these are the modeled overall energy savings compared to what was actually in the building. Oftentimes our utility partners would need to, or wanted to provide an energy incentives, but maybe it was a 30-year-old piece of equipment that was needed to be replaced anyways. Well, what do we do for energy savings then? Same process, start with actual data versus actual weather data. And then we take that and we use that, all the same inputs, but we just improve the efficiency of the equipment to meet code minimum. So maybe the boiler wasn't code minimum anymore, or the compressor wasn't, or the air conditioner wasn't code minimum. Then you just upgrade all the equipment, but you still have a calibrated model. So this is what we call incremental energy savings. So you're still able to use actual collected field data to build a calibrated model and then apply it to new equipment, but you still have all the same loads and same kind of schedules and everything. All right, home stretch here, final thoughts, and then I'll stop talking. Just a link of a bunch of resources that have real data, both reports kind of summarizing the data, and usually many of these will actually have availability to actually download the data and find it. I like that. So BetterBricks has a bunch of them, some great energy modeling guides that we've kind of learned over the years, some helpful hints for building simulations. I mentioned that residential heat pump database, the DOAS site, lots of data there. Minnesota CE has some great reports. I don't think they have raw data or process data here, but they have some really good white papers that I like. And then here's a huge one, not as cold climate related, although there are some cold climates in California, but this Tech California database, it's a heat pump database, a lot of residential space heating and heat pump water heaters, but just like, I don't know, there's like a million data sets in here. So it's a huge database. Could be relevant for like multifamily applications, things like that. Yeah, one more pitch on very high efficiency DOAS. I think it's a great application in small commercial buildings, separating ventilation from heating and cooling loads, eliminating ventilation loads, and then right sizing the heating system. These are some key principles that we found that are very important for performance in small and medium commercial buildings. All right, last slide, I believe. Just to reiterate some of the lessons from the field, air source heat pumps perform extremely well, even in cold climates. It gets fairly well established. You just have to find the right equipment. Sometimes that's not that easy to do. Certainly not that easy for an end user or small contractors to be able to find the right equipment, especially in rural places. That's a challenge. Air source heat pump field performance is often much better than what building simulation curves have built into them. It's oftentimes a little worse than what the manufacturers produce in the lab. But if you have, the standard curves, they're oftentimes significantly going to underestimate performance. Whole building energy model often significantly underestimates the energy use of real buildings. So the DOE prototype models, they oftentimes have very idealized envelope models that have very low infiltration, and those significantly underestimate the heating load. So many times when you just take the standard models, it's going to show an EOI of like 10, HVAC EOI of like 10 in a cold climate. And you're like, I've never seen an existing building have an HVAC EOI that low. And that's just what the standard is. And that's partially driven by codes, because codes are always trying to drive the standard code minimum system performance up, because that's how they show the codes are having energy savings. Anyways, that's just another thing. That's why calibration is helpful. HVAC systems are chronically oversized. Wealth of heat pump data, I've mentioned that a few times. And then this last one, simplify models. That doesn't, not just building performance models, but any type of models that you use. Simplify as much as possible, but not too much. You still have to be able to like answer the question that you're trying to solve. But when you're trying to figure out what's wrong with a model, if it's so complex that you think it describes every single aspect of the system, that's great. But when you come back and try to calibrate that model, or whether somebody else tries to come in and figure out what your model is trying to do, it's very difficult to make any sense of it. So that's just what I encourage you. If you use any type of models, whether it's whole building energy models, whether it's simple models in your professional life or simple models in your personal life, simplify, just not too far. So that's one of my favorite things. So, all right, and that's all I got. Thanks for listening.
Good for 10 minutes for questions.
Okay. Jonathan.
Yes, you mentioned when we were looking at the Trapper Creek dorm, you said that if the system's designed well, you don't necessarily need a cold climate heat pump in a cold climate. What gets the Jordan Pratt designed well stamp of approval system?
What does? That's a good question. I mean, I'd rather have any heat pump rather than electric resistance in almost any climate. So that I would say, if you can get it done and it makes sense economically, like that's my stamp of approval. But do you mean like how cold, or
What are the factors that drive whether how well that's going to work?
how well that's going to work? That's a good question. So certainly the ability, like the kind of the cutoff when the heat pump stops being able to perform at least somewhere near nominal capacity. A lot of old ones will kind of cut off at 40 degrees, and then in that case you may not have any energy savings relative to like a different fuel system. So that's probably the biggest thing. It's where the cutoff temperature is, what the manufacturing curve is saying.
You have the slide where you compare GTUs, kWh therms. Do you have a comparison of average versus cost?
Yeah, that I did have cost on there.
Oh, there was.
So this is obviously a single cost value. Yeah, so right here, it's not big, but gas system, $1.25 to deliver a therm.
Right, but that's operational cost, right? You have like first cost installation.
Oh, first cost installation. Oh, I see. Totally dependent. These are very generalized. Those could be in a residential space heating application or a commercial water heating application. So I try to make it very much just about like,
The CO.
does a heat pump make sense compared to gas, because gas is so much more cheaper. And basically the point is, whatever the application is, somewhere around this number in most places. It gets a little wonky in certain spots. That's kind of your break even in terms of cost and emissions. First cost totally depends. If it's a residential forced air furnace heat pump versus, or furnace versus a heat pump, it might be, 10 versus 15 or 10 versus 20 in some places. If it's a water heater, right, it might be 700 versus 1300. And if it's an industrial boiler, it might be like 500,000 versus 5 million. You know, it's like, it just depends on the application and what kind of what kind of equipment's available. Yeah.
It's not as easy.
It's not as easy of a first cost line. Yeah. Also actually quite regionally dependent, and even within regions, like the equipment providers and the contractors, like some people really know how to do it well, right? Like very competitive quotes with heat pumps, some places it's just hard to find.
Okay, thanks.
We recently had a commercial customer that was looking at these different options for water heating. And they actually ended up installing an electric boiler. They're kind of like, well, look at all these better economics, energy saving, et cetera, what was going on. And one of the things they said as well, there was installation considerations that led to us going with this boiler versus a heat pump or some of these other options. Any insight into what they might have meant by that?
Yeah, absolutely. I mean, if you're talking about commercial water heat, oftentimes we're in boiler rooms. And so we've got to find somewhere to get that heat source. And so if we have a big brick mechanical room, it may not be easy to find a place to put your outside air unit, your compressor. So that's certainly a challenge. And there are certain technologies, like we did a condensing rooftop unit field study, and it was great, performed super well. But like rooftop units, what's so beautiful about them is you like pull them off, put them back on, and it's done. It's done with a day with a crane, and it doesn't cost you anything, and you got to heat again. With condensing, you have to figure out what do we do with the condensate, which isn't like air conditioning condensate. It's a little bit acidic, so you got to either run that through a neutralizer, or you got to get it into an approved plumbing location. Anyways, all that to say is that, and many other technologies, there are very important challenges, and that's one of them for commercial water heat in particular. That being said, we've done many in those exact same buildings where if you find somebody who's like, oh yeah, I've done this before, I can do that. You just punch a hole in the brick and run, do a split system instead of a package this water heating design. You run an outside unit out there, run your indoor unit in the boiler. Outdoor unit is totally rated for outdoor performance. So it can absolutely be solved. But sometimes when you, as a building owner, right, you go to your preferred contractor or your preferred design engineer, and you ask them, well, what have you seen before? If they haven't seen that, often they say, oh, it's going to be way too expensive. And so sometimes it takes a little work or a little support, like from a third party, to be like, all right, well, let's go explore some solutions. Let's see who else has a product that might work in that application. So definitely a challenge. It's not always easy. Water heat in residential also can be a challenge. What do you do with that cold air, depending on where it's located? But some applications, it's just a piece of paper.
Any questions online? Feel free to unmute yourself.
I got a question. More of a not related to this too much, but Jordan, are you related to Jeff?
Yeah, that's my dad.
That's what I thought. Tell him Mark Jerome said hey.
All right, I will. I think
Right on. Good to see you again.
Good to see you too.
Yep. And good stuff, man. I really appreciate the resources, the info sharing. So thanks.
Appreciate it, Mark.
Hey, Jordan, this is Todd Greenwell, Idaho Power. Just a quick question. Appreciate the presentation. It's good material. On this chart you're showing here, that dollar per therm in the box, is that the assumed delivered cost to an industrial customer that you're using there?
Oh, no, I'd say that would be more like half of it. I was trying to, I forget the first time I made this slide, I was trying to do round numbers because, I'm not so good at math, so it's easier to kind of convert. But I was kind of thinking of like a urban residential application in this one. But my experience is usually if we go in industrial, that $1 therm is more like 60 cents a therm, and our 12 cents a kilowatt hour becomes 6. So spread is close in most applications. I think you're right. In industrial, that number may need to be maybe a little lower or a little higher actually, because nonetheless, it's a good question.
Yeah, that's fine. Yeah, because I mean that spark gap is the talk of the town, and that's everything. I mean, at what point are you at parity with BTU production using electric energy, versus fossil fuel But I know that on EIA, I used 72 cents for the residential delivered therm cost. And that's why
Yeah.
when I saw a buck, I was trying to figure out where that came from. 12 cents is what we publish at Idaho Power for the average KWH costs for residential folks. But I just, I mean, rerunning these numbers with really what we're paying out here for different energies is this a critical slide. Basically, it supports the business case to promote or not promote what Chris called, earlier when you mentioned fuel conversion scare tactics or taboo conversations. So anyway, thanks for the presentation.
I think it's worth considering. And anytime a customer asks me, I'm like, let's look at all the options. Like, that's what we should be doing. I'm willing to share this spreadsheet. It's about like 4 rows and 3 columns. You can put in whatever numbers you want.
Yeah, no sweat. No, it's just want my clarity for myself. Thank you.
Yeah. Thanks for the question, Todd.
Any other questions? Okay,
So just looking at the data points in different states on the earlier slides there, you got some nice Montana, flooded in Oregon and Washington, CD and Idaho.
That's why I moved out here a couple of years ago. Some more field tests. It's slow going. Been giving us too much work. Good point. I think some of that's just based off of availability, customers. A lot of the sites that we've done have been from utility partners like energy efficiency implementers that have found, a small school that needs help and they want to help make a project happen. So a lot of it's just opportunistic, like where we have people bringing us projects to look at. But NIA is always looking for more demonstration projects, and so like anytime there's a potential project, I think it's great to come to me, and I can try to relay the message to try to find funding for support. It's not always there, but if the application is interesting enough to 140 utility funders, oftentimes you can make a pretty good proposal. Yeah.
Hey, Jordan, this is Todd. One more quick question. I was kind of curious, are you planning or are you currently involved with Energy 350 with doing demonstration projects with waste heat recovery to produce industrial heat pumps, with the 200 to 600 degree temperatures that the industrial plants use? Not so much food processing and paper and pulp that are lower temperatures, but there seems to be a kind of a shortage and a growing need for industrial heat pumps that are actually, possibly needing to use waste heat to produce the output temperatures needed for a lot of the higher temperature processes. Are you seeing any of that in the United States, or at least?
So in Oregon, we've done lots of industrial heat recovery applications, none for high temp industrial heat pumps that I know of. I know we have 2. I was just talking with Chris. We do have 2 studies that we have, waiting for a customer to go forward to in industrial heat pump applications that we would love to happen, so we can have some, real world performance. But I don't know a lot of them. I know a few of them have been out here. One in like Vancouver, Washington. ACEEE hot water forum is always where I go to like learn about the fun new projects that are happening. But no, I don't know of any in Oregon we've done with industrial heat pumps yet.
Yeah, just curious. Thank you for that. Appreciate it.
okay, there are evals in front of you. If you could please fill those out, we appreciate your feedback. And thank you very much, Jordan, for coming.